Okay, this is the sixth chapter, chapter 6, large random sample. So this chapter is going to be shortest among all of the 6 chapters, right? So we are very near to the end of the course already, okay? And in this video, we are going to talk about the law of large numbers. So let's say this chapter is about in this video, we talk about the law of large number. And in the next video, we talk about the central limit theorem. And these 2 theorems will be used if you study somewhat like the mathematical studies, in which we do not cover here because we talk about the probability theory. But this one serves as the basic foundation, okay? So give you a sense of what the future might be. So the motivation, when we summarize the information, let's say in the last video, when we talk about, let's say, taking the data from the set index in order to see the patterns, right? So the summary data that we usually have, that we usually want to construct, is the average of random sample. Let's say that we have what? We have xn bar, right? Is equal to x1 plus x2 up until what? Up until xn divided by n. Okay? And this is a sample. And if you look at it carefully, xn bar is the random variables too. Why? Because each time you collect a set of data, let's say a set of n observations, you are going to get different n sets of the observation, but usually you could get only one set, right? Because you combine all of available information into your study. But let's say if you were to collect multiple times, surely you could get different xn bar. So the sample mean, this one is called sample mean. Sample mean is useful for summarizing the information in a random sample in much of the same way that the mean or the probability distribution summarizes the information in the distribution. So let me start with the Markov and Chebyshev inequality, okay? The Markov inequality says that suppose that x is a random variable such that it is positive, it is non-negative, right? So this one means that this variable is what? X is non-negative, right? Then for every real number t, this one holds true. So this one is the upper bound, okay? This one is the upper bound on the tail probability. Ex over t is the upper bound, okay? So how do we prove this? Okay, E of x is sigma x f x. So you could split into x less than t or x greater than or equal to t. Since x is non-negative, okay, you could get only this stuff because this is positive, right? And it is greater than or equal to t times this one. It is t of probability of x greater than t, but if you look at it carefully, you could get something like this, right? So we divide t by both sides, you could get this inequality. Okay. So Markov inequality, what does it say? The Markov inequality is trivial for t less than or equal to e of x, surely, okay? Because it's gonna be 1. So nothing too fancy here. It's found that for the Markov inequality, that for every non-negative random variable x whose mean is 1, the maximum possible value of probability f x greater than or equal to 100 is 0.01. For example, when probability of x equal to 0 is 0.99 and probability that x equal to 1 is 0.01. Okay, so this one is not tight because 0.01 is not true for most distribution, let's say, especially for the normal. Okay, but it's true for some distribution. So let's say could we make this bar a little bit sharper? There is Markov is sharp, but sharp in the sense that if we know only the mean, okay, only the mean and the t, what bar should we get? But if we have the variance too, if we have the variance into the information, this one is a little bit sharper than the Markov inequality. Okay. So this one is a tail. It's a tail probability. But the tail probabilities of what? Of using variance instead of the expectation. Okay. How to prove this one? Because this one, okay, you could what? You could take power 2 on both sides. And then what? E of y is variance of x. And t squared go to 0. Okay? So it's just the extension for the Markov inequality. So what does it say? For example, the probability that any given variable, random variable will differ by its mean by more than 3 standard deviations can exceed 1/9. It can also be shown that upper bound is sharp in the sense that it cannot be made any smaller and still hold from distribution. So it's not that sharp 1/9, but it's good. It's good for us to proceed into talking about the law of large number. Okay, and this is a sample mean. Okay, and from the Chebyshev inequality, we can construct this bound. We can construct this bound. Okay, so x n bar differ from mu greater than or equal to t, less than or equal to sigma square over n, because this is the variance of x n bar, right, over t. So if n is equal to infinity, let's say keep t fixed, okay, keep t fixed, and let n go to infinity. What does it mean? This one is gonna be go to 0. That means what? That means as n increases, x n bar is closer and closer to mu. And this one is very similar to law of the large number that we are going to see next. Okay, but first, we want to define this first, convergence in the probability. Okay, a sequence C1 of Cn on the number converge to B in probability. Okay, so convergence and convergence in probability is a little bit different concept, in the sense that if you talk about the convergence, the pure convergence, okay, the pure convergence. So let's say that okay, in the sense that if we have epsilon, so the epsilon is a little bit like the radius, right? So let's say that if it converges to B, what happened? So we define B plus epsilon, okay, and B minus epsilon. We construct this kind of bound, and we say that, okay, we say that there is the n, there is the n, no matter how far they are, okay, there is the n, such that, okay, let me use the capital N, such that for n greater than or equal to n, Hn is in the set of B minus epsilon and B plus epsilon. So this is the intuition of the convergence to a number in terms of the sequence, but in terms of the probabilities, it's not certain like this, right? So for the convergence in the probability, it is such that, okay, it is such that we keep the epsilon fixed like this one. So every epsilon greater than or equal to 0, but when we consider this, we consider as a fixed number, as a fixed parameter, okay? The limit of the probability that absolute Cn minus b less than epsilon when n go to infinity equal to 1. That means it is very similar to the sense that there is the n such that if n is greater than or equal to big N, it is the probability that it is less than epsilon is equal to 1. That means what? That means for infinite n, the Cn will be in b minus epsilon and b plus epsilon surely, because the probability is 1. Okay, so it is a different concept, but we can find similarity between the convergence of the sequence and the convergence in the probability too, because we cannot say about like this because the Cn is the random variable, right? Okay, we could use the shorthand notation like this: Cn converge to be in probability. Okay, and this is the law of the large number. So let's look at this statement carefully. Suppose that x1 up until xn form a random sample, form a distribution for which the mean is mu and the variance is finite. Let xn bar denote the sample mean. Then xn bar converges to mu. Okay. Let's see the proof. Okay. So for the Chebyshev inequality, we can apply to this because the Chebyshev we have greater than or equal, right? Okay, let me draw some steps first. So in the Chebyshev, we have something like this. For the Chebyshev, okay, okay, and we have greater than or equal to epsilon. It's gonna be what? Square, right? And then we have sigma square over n, right? And then times epsilon square. However, from this one, it is straightforward, right? From this one, you could get from greater than or equal to less than here. And then for this one, if we let n to the infinity, this one is going to be 1. That means xn bar, the sample means, will converge to mu in probability. It follows that there is a high probability that xn bar will be close to mu if sample size n is large. Okay, and this is, let's say, the extension. Okay, so if Cn converge in probability to b, then if you construct the function, g of Cn will converge in the probability. Okay, this is a typo. Actually, it's probability to g of b. Okay, and the histogram. Let x1 and x2 and so on be a sequence of ID random variables. Let c1 less than c2 be two constant. Define y I equal to 1. Let's say if xi is the indicator, we call I as the indicator random variable. Okay, and yi equal to 0 otherwise. And then let yn bar is gonna be something like is the mean of the indicator random variable. So this one converts to the probability that x1 between c1 and c2, right? Because e of y is what? E of y is this probability already. So it's like the corollary, okay? It's straightforward that this sample will convert to the probability to this probability here, okay? And that's the end of lecture 42, okay? And in the next session, we are going to talk about, let's say, one of the important theorem in statistics called central limit theorem. So see ya.